What is the biggest star in the universe? How come I don't understand the Fermi paradox? And can stars swap between galaxies? All this and more in this week's question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down in the YouTube comments and I will gather a bunch of them up and I will answer them here. All right, let's get into the questions. Thanos sustainable. You've mentioned that the biggest star that we know of is around 150 times the mass of the sun, but I've seen animations that depict really huge stars, enough to engulf the whole of our solar system, and then some. Are they misleading, or are there stars out there that really are indeed just 150 times the mass of the sun, but are much bigger due to a much lower density? Yes, the largest star and the most massive star are like two completely different concepts that you're really going to need to keep in your mind and keep them separate because there's different factors that lead to both of those. So let's start with the largest star. And the largest star that we know of, and this is like at the time that I'm recording this episode in March 2024, but this is changing all of the time. And so I refuse to be pinned down. If you come at me in a future video and go, Fraser, you mentioned this star and you said it was the largest star, but it's not the largest star. This is the lowest. I know astronomers are continuing to work, and yet this video is just locked in the past. And I can't go back and I can't update it and I can't put new voiceovers over top of it. So the words that I'm about to say for what the largest star and the most massive star are going to be wrong almost the second that I say them. Deal? All right, so the largest star that we know of right now, it's called WOH-G64, and it is a gigantic star in the Large Magellanic Cloud. It is a red supergiant, and astronomers have measured it at about 1,540 times the size of the sun. If you take the orbit of Saturn, this star almost reaches the orbit of Saturn. We talked about Betelgeuse, which would gobble up the orbit of Jupiter. This will almost reach the orbit of Saturn. And this star is pretty much at the largest, theoretically possible, biggest star. I interviewed an astronomer a couple of years ago and I asked her this question, like, what is the biggest possible star? And this was before WOH-G64 had been discovered, and it was about 1,500 times the size of the sun. She figured like that's about as big as these stars can get before they're just going to be too diffuse and they're just not going to be able to form any larger. And yet the mass of this star is only 25 times the mass of the sun. So you've got a 25 solar mass star that is puffed out to 1,500, more than 1,500 times the size of the sun. And so, you know, mass, it's a very not dense star. Now let's go the other direction. Let's think about the most massive star in the universe. The most massive star that we know of, again, same caveats, is BAT-99, also located in the Large Magellanic Cloud, and it has 226 times the mass of the sun. So it is 10 times more massive than the other star that I mentioned, but it only has 37 times the size of the sun. So it is dramatically smaller. So what's the difference? Why? It all comes down to temperature. So with a star like BAT-99, you have got a star that is relatively young, earlier on in its evolution. It is incredibly hot, and that makes the surface temperature of it more than 10,000 Kelvin. I don't know the exact temperature. I'm just sort of going from memory now, but it's going to be ludicrously hot. But with the red supergiant, the star is a lot cooler. And when you get this star that's a lot cooler, these stars tend to be a lot bigger, and the surface temperature of them is much lower, like red. So it's like around 3,500 Kelvin. And so the cooler stars can get vastly larger than the blue supergiants that are younger. And like even our sun, when our sun, which is only the mass of the sun and the size of the sun, when it runs out of fuel in its core, it switches from hydrogen to helium. It gets this increase in temperature in the core. It puffs out the outer layers of the star, and it will probably engulf the orbit of Earth. And yet it's the same star, same material. It's just that more temperature going on in the core puffs out the outer layers and it engulfs the orbits of the Earth. So Yeah, you can have stars that are incredibly large, but not super massive. You can have stars that are incredibly massive, but not super large. And that's the universe for you. I hope you enjoyed that appetizer, because now we're going to get into a bunch of Fermi paradox questions. And this just always happens whenever I tackle a Fermi paradox question in one show, then I get just a deluge of Fermi paradox questions after that. And I feel responsible somehow. So I've got to sort of clean up after myself. So I'm going to give you 3 Fermi paradox questions. Here goes the first one. Mark Allen. Hey Fraser, every time you mention advanced civilizations colonizing the universe, you'd say they'd be doing it at close to the speed of light. But surely their von Neumann probes have to stop to do their thing before they can replicate and move on. So they can't be expanding close to the speed of light. Right. So obviously you can't go the speed of light. This idea comes from the interview that I did with Robin Hanson and his concept of grabby aliens. And we're going to talk a little bit more about grabby aliens in the next question. But I just want to sort of cover this first, which is that when we think of a civilization expanding out into the cosmos, one of the things that we sort of need to understand is that the universe is expanding away from us faster and faster. And that already, we know that the universe is, say, 92 billion light years across. But in fact, most of that universe is completely unreachable. Even if we could go the speed of light, we could never catch those areas. Only about 4% of the entire observable universe is within a region of us that if we set out tomorrow at going 99.999% the speed of light, we could actually reach those places. That is the accessible universe as opposed to the observable universe. And it's a tiny amount. It takes us out to about 1 billion light years away from us. And so any future civilization that has arrived on the scene is realized that they're in this universe that is expanding and they really want it all. They've got to really want it. Then they'll understand that the very first thing that they need to do immediately is send von Neumann probes, these self-replicating robot probes, to other star systems as far as they can feasibly do it. Now remember, once you get a spacecraft up to its cruising speed at 99.9 whatever percent the speed of light, then it'll just coast forever. And theoretically, you've got some way figured out that it can slow down when it arrives at its destination. And yeah, maybe you're going to lose some of those galaxies over the cosmic horizon, but you're going to get some of them. And so this idea of grabby aliens, of aliens sort of reaching out, you can imagine they might do this in waves, where they will first send the spacecraft at the most distant places, the places where if they don't act now, they're going to fall over the cosmic horizon and they will lose that territory. And then they'll send them to the next farthest ones and the next farthest ones. And what that will appear as is a sphere that's kind of being filled in from the outside in, because they are attempting to plant seeds in all of these galaxies across the entire universe. Once one of these probes has arrived in one of these galaxies, and then it's going to end up on a star system, it's start manufacturing copies of itself, it's going to, as you said, do its thing, and it's going to attempt to colonize the entire galaxy. But from an outside observer, you would see that wavefront of these probes moving out through the cosmos. And yeah, it might take, let's say if we wanted to send a von Neumann probe to the most distant galaxy that we can reach, and say it's 800 million light years away. So this probe has got a journey for 800 million years from our perspective. Now it experiences dramatically less because it's going close to the speed of light. And then it arrives, reaches the star system, and then it begins to self-replicate itself and would fill the entire galaxy within just 1 million years, at going 10% the speed of light. So from an outside observer, it would appear that these galaxies are just appearing and within just a very short time frame are getting completely colonized compared to the distance that are being traveled. And that's kind of what Robin Hanson was envisioning of this expanding sphere of influence from some civilization. I'm sure you noticed the Star Trek planet name that appeared above my shoulder. This is a way for you to vote, for you to tell us what you thought was the best question, the best answer, the best hybrid question answer. And the winner this week was from Antonis Karpanos, where should I send my scientific discovery to be checked or promoted to be known to other scientists? So thank you everybody who voted for that question. Now we're going to put a different Star Trek planet name up above my shoulder for every question in this entire show. We're going to put the names down in the show notes so you've got a nice reference. And then at the end of the show, after you've watched the entire episode and you've like really thought carefully about what was the good question, go ahead and put that Star Trek planet name down in the comments down below, and then I will gather them up and we will celebrate the next one next week. Cargo Runner 9960. I don't understand the concept of the grabby aliens. Why would any species want to convert or consume every resource in the universe? So this is one of the other common questions that we get about the grabby aliens. It's just like, why would they want to do this? Well, like, why do we assume that all the aliens are going to want to consume all of the universe? And the answer is you don't assume that. You assume that 99.999% don't want to, that they want to stay home and they want to live in their simulations and their holographic universes, and they want to just contemplate transcendent peace, and they just want good, nice things and just to be happy. And they just stay in their small system and they never go anywhere. But it's that 0.001% that you've got to keep your eye on. The one that says, I want it all, please. And I can, because you've got all these neighbors and they're just going to sit back and they're going to live in their simulations and they're going to think about philosophy, and we're going to go for it all. We're going to try and grab every available piece of energy, every watt of energy, every atom, and we're going to add this to our collective, like the Borg, right? And you can say, whoa, that's okay, scary, sure. But then sort of you can imagine other civilizations that were like, well, we did want to just sit at home and consider our own benevolence, try to transcend to a higher level of peace and prosperity. But we're worried about that civilization that's going to try to grab it all, the grabby aliens. So we had better grab first to be prepared so that when the grabby aliens show up, we're not just going to roll over and be conquered by them. We're going to put up a fight. And so even if you aren't the ones who are going to try to grab the entire area for malevolent reasons, you can imagine sort of game theory reasons why other civilizations might want to do the same thing just for protection. Because being a powerful civilization gives you the leeway. I've been reading the culture books fairly recently, and there's this attitude that the aliens or the people of the culture have towards less advanced civilizations. You know, they don't want to cause them any harm, but they also don't want to let them just be jerks. And so they have such advanced technology that whatever these other civilizations might want to do to them is meaningless. It's harmless. They can't do anything. They make jokes in the books about how various people in the culture have fun by trying to tamp down self-replicating robot probes that are trying to take over the Milky Way. And so you can imagine either you become the grabby alien, or you realize that the grabby aliens are enough of a threat that you attempt to become more powerful than any potential grabby alien. Either way, you need to acquire resources to be able to do that. Amazing Things 3. Why does everyone skirt around the answer? Because it's a human answer and aliens are not human. We expect them to do human things, which they will definitely not do, so we can see them because they do not do things our way. Yeah, this is another common pushback I get about sort of us trying to envision what advanced civilizations might want to do. They say, well, like we're human beings. We're looking at everything from a human perspective. How could we expect the aliens to do the things that we human beings are going to do? And so there's kind of sort of two answers to this. One is that maybe they don't, that most of them won't. But all it takes is the 0.001% that's kind of like human beings to go for it, go all in, try to take over this galaxy. So that's one thing, is that you're only going to see the expanders. You're not going to see the philosophizers, the transcenderizers. You're only going to see the expanders. And so it's sort of like a survival bias that what you see are the ones going for it, trying to take it all. But then the other thing is that in this universe, we assume that we've got a couple of basic things that we all share. There is energy, there's light coming from stars and maybe other energy sources. There is matter that is made up of those stars in the planets, of the asteroids, of the comets, things like that in the galaxy. And it's the equivalent of a limited amount of sunlight falling into a forest, a limited amount of nutrients on the forest floor that the various trees can use for growth. And they are sharing this, they might have different species, but they're all sharing the exact same resources. And so we live in this physical universe, potentially with other civilizations, and we share these physical things with them. And so the universe will end up being resource constrained. And so one possibility, whenever you get resource constraints in nature, you get evolution, you get competition, you get human beings doing human being stuff. And so it probably won't be humans, but you can expect that some percentage will behave in ways that are similar to us with respect to their environment. Dark star 420. Isn't there a star heading towards us from the Large Magellanic Cloud? It will never get here, but it's really cool. I have no idea. I don't recall a story about a star heading towards us from the Large Magellanic Cloud, but it's almost inevitable that there is one. And let me tell you why. And that is because the Milky Way is ejecting stars at various escape velocities. And at this point now, astronomers have discovered almost 100 stars that are on trajectories that are going to take them out of the Milky Way. They're leaving this galaxy and they're never coming back. And there's a couple of ideas on why that might be. One is that you can imagine you have two stars that are in... Oh, stupid microphone. All right. You have two stars that are in a binary relationship, two stars going around each other, and one of the stars explodes as a supernova and disappears, and then the other one is now slungshot out of the system and is now heading on a trajectory that's going to take it outside of the Milky Way. The other scenario is that there are stars that get really close to the center of the Milky Way. They come close to the supermassive black hole at the heart of the Milky Way, and then they get into some sort of three-body interaction and they get ejected out of the Milky Way at extremely high velocities, like 1,000 kilometers per second, upwards of 1,000 kilometers per second, which is very fast. And the Large Magellanic Cloud, I just mentioned the biggest star in the universe that we know of, the most massive star that we know of, and both of those are in the Large Magellanic Cloud. And that's because the Large Magellanic Cloud contains the most active star-forming region in our neighborhood, places that are vastly beyond what we have in the Milky Way, with very large stars. And so you can imagine some of the largest stars, maybe in the Tarantula Nebula, have exploded as supernova and kicked out their companion stars. And so there's a piece of research that came out today as I'm recording this, and by the time you read this, we'll probably have reported on it in Universe Today, and I'll bet you it's going to make it into Space Bites this week. And that is that astronomers are pretty sure that there is the same thing happening from Andromeda, that there are stars on escape velocities leaving Andromeda in our direction, and vice versa, that there are stars that are leaving the Milky Way that are headed towards Andromeda. And so it is entirely possible, because these stars are going faster than the galaxies are, as the galaxies are moving towards each other. They're destined to merge in several billion years from now, but they're both sending stars on escape velocities outside of both of them, and yet some of them are going to go towards the other galaxy, and then those stars can get caught in three-body interactions. And so there could be stars in the Milky Way that came from Andromeda and vice versa. And those stars could contain planets with life on them. And so you could imagine that, although that would be pretty awful to try and be on one of those star systems when your star beside you goes supernova, but who knows? Who knows? And so we could have stars that came from galaxy to galaxy. And so maybe it's a whole different way to think about how life could move from galaxy to galaxy. Anyway, blows the mind. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Igor Bizarny, Hoppy Rabbit, Avery Buell, Rusty, Matt McHugh, David McDonnell, Janice Smith, Ben Mills, Brett LaRue, Martin Trevino, Not Sure, Joker. Join the club at patreon.com/universetoday. Sam Powell. Do you ever feel frustrated about how slow the process of scientific discovery is? Don't you wish we were a little bit more audacious and daring? I think everybody experiences that feeling when you're stuck in the middle of it. Like, think about how long it's going to take to wait for season 2 of One Piece. Feels like it's going to take forever. Think about how long it takes between Stanley Cups. Just feels like it takes forever. And just like when you're living life day to day, this stuff takes forever. But from my perspective as a science journalist, as I'm reporting on various missions, I get overwhelmed. And yes, I would love to sometimes fast forward into the future when the Habitable Worlds Observatory is built, or the Solar Gravitational Lens Telescope is built, and we're getting those observations from these other star systems. But I'm also completely overwhelmed by all of the discoveries that are happening every single day. So like, I have to go through 1,000 potential news stories every single day. Now, the bulk of them are very low grade stuff that I'm not going to probably find anything interesting. Like, there's about 130 papers posted just to archive every day that I look through to find anything that I think is going to be really interesting. Like Andromeda Milky Way sharing stars, as an example. You heard it here first. Just remember this. You know, there were a lot of missions like that launched that I thought, this is never going to happen. Like, I remember when they launched New Horizons to Pluto, and it was going to be a 10-year cruise phase. I remember when they launched the Rosetta mission to Comet 67P. And again, it was going to be this like 10-year duration where the spacecraft had to go into hibernation, waiting for its flyby. And you just sort of park that in your brain, and then you just go back to all of the amazing things that are happening every single day, every single week, every single month, every single year. And then suddenly time creeps up and the 10 years have passed, and now you're 10 years older and 10 years older, but you know, you were kept entertained in that meantime. So no, I'm not frustrated at all. In fact, I often feel like it's too fast, it's too much. I can't wrap my head around all of it, especially with the kinds of progress that's happening in computers, artificial intelligence. A lot of that, like, please slow down. Give me a chance to digest what's going on. Could we be more audacious and daring? I think that being audacious and daring is the result of what you see after all of this dust is cleared. But you forget all of the back and forth that happened. And when you look back, there's some great biographies about scientific discoveries, about people fighting over dinosaur bones, or whether or not plate tectonics explained the continents on Earth. And it took decades and decades for people to have these ideas, to fight over them, for aging scientists to die before other people accepted their ideas. And now the cycles are going a lot faster and a lot faster and a lot faster. And a lot of it just feels almost overwhelming. So no, I think if anything, I kind of would like certain aspects of science to slow down a little bit, just so I have more time to digest what's going on. Jacob Soley. Since we can't see anything before the cosmic microwave background was emitted, how do we know what was there 300,000 years before that? How do we know there was any time at all? The cosmic microwave background, this is the first point in the universe when everything had cooled down to the point that light could finally escape, that the universe became transparent. And this incredible discovery was sort of made by by accident, where astronomers had built this radio telescope and they were scanning the sky and they got this signal that they were detecting that matched predictions from other astronomers that if the universe worked the way that we thought it did, then you should see this hum, this background radiation. And the way this works really is that, back in the 1920s, Hubble discovered that galaxies are moving away from us in all directions, that the universe is expanding. But really, a better way to describe that is that the universe is becoming less dense over time. And so if you run the clock backwards, then those galaxies would be getting closer and closer to each other and closer and closer to each other. And eventually, you would get to this point where all of the matter in the universe was so close together that it would all be ionized. And then there would be this transition from when it was all ionized, completely opaque, to when it was transparent and light could finally escape. And that it should give off this very specific wavelength of light that astronomers were able to detect. And the cosmic microwave background is the most beautiful piece of evidence that we live in this expanding universe. But then you just take the numbers and just keep going. That if you know the expansion rate of the universe and you're able to measure it back in time, and you're able to measure to this point when the universe was so dense that it was opaque and that it was all just ionized hydrogen and helium, then you can just keep running the clock backwards. You just imagine the universe a little more dense, and a little more dense. And eventually you get to this point where the entire universe is like the density of a star. And you can calculate the amount of time that would take from when it was the density of a star to when it was the density when light could actually escape into the universe. And if you imagine that the universe was the density of the star, then you can calculate how long it was like the density of the interior, the core of the sun, right? And you say, oh, it was about that way for about a dozen minutes, about 12 minutes. And that it was able to turn hydrogen into helium during that time to create about the ratio of about, say, 75% hydrogen and 25% helium. And that's the ratio that we see of hydrogen to helium in the universe. So not only do we have that time when we're seeing this radiation, this first light from the universe, and then you do the math and you get back to this time when the universe was like the core of a star, you get those ratios, which is the second big pillar of evidence, was that, okay, yeah, it once spent time like the core of a star, then it spent time like the surface of a star, I guess. And you could just keep running the clock backwards. Then we know, okay, then there was a time when you actually didn't have atoms, you had the subatomic particles. And then you could just keep going. And you could find this time when the various forces merged together, and you had the electroweak force, and you had the merging with the strong force. People haven't been able to figure out how gravity fits into this. And you can just keep doing the math, and that takes you right to the moments after the Big Bang. And that's as far as we can go. That's as far as the math can take us. The CMB is just beautiful when you just think about what it's telling us. And it's just math. It's extrapolating what we see today, making predictions, seeing what you were hoping to see, and then continuing that process right to the Big Bang. The Canadian Space Advocate. Do you think there's more room for science reporters or debunkers? I don't understand. Are you saying that is there more room for science reporters, or is there more room for pseudoscience debunkers? Or is there more room for science debunkers? I'm not sure how much science debunkers we require, because, hopefully if it's science, it's not bunk. But you definitely want bad science debunkers. One of the problems that we have right now is that we've got the media landscape is fracturing. So in the olden days, when I started doing Universe Today, there were dedicated space journalists in a lot of the major media outlets. You had Miles O'Brien at CNN. You had people at Florida Today. You had people at MSNBC, Alan Boyle at MSNBC. You had a bunch of dedicated reporters at all of the big news outlets. And when you would go to the Kennedy Space Center to watch a space shuttle launch, there were trailers for each one of those outlets, there's a CBS trailer and there's an NBC trailer, there's an ABC trailer. And I walked past all of these trailers that were mostly empty when I was there last time. And then people started to cut away their ability to report on science. There was no longer a space reporter at these large media agencies. Maybe you just had a science reporter. And so the science reporter could tackle biology news, health news, and have to do some space news, but they're not going to have that same level of knowledge. And then you got even the science reporters were no longer necessary and were laid off. And so now you've got the weather reporter who's having to do some science news, or the environment reporter, or the health reporter is having to tackle some of this stuff as well. And so they're just not going to know. But at the same time, I mean, these big media agencies are running out of money. They're, you know, unless you're the New York Times and a couple of other big agencies, they've got a business model that just isn't sort of carrying the day and helping them be able to increase the quality of their news reporting. And I think what you're seeing then is a big success in the smaller news agencies like Universe Today. I mean, what are we? We are me and maybe a dozen reporters who specialize in space and astronomy. And that's all we report on. It's all we know. And so we're able to specialize and stay current and up to date and make sure that our information is accurate. And I think there's still a ton of room at the bottom, you know, not like bottom, like a ton of room like for the small guys. And so if you want to be a science reporter, you can do great science reporting, start a newsletter, be able to actually earn a living from that newsletter and just keep going, which is sort of like even a smaller version than what we do with Universe Today. So I think there is still a tremendous amount of opportunity for people who want to do this. And there's huge hunger for it. Like, remember that, everybody loves space. Everybody loves this stuff. And yet the quality of the reporting isn't able to keep up with the demand, the hunger. And when you look at these smaller folks that are heavily covering rocket news, I mean, just every single thing that SpaceX is doing, there's like 10 channels on YouTube, every tanker movement, every barge arrival, every bolt attached, they're all over it from the sky, from Boca Chica. It's kind of amazing. And that just sort of shows that the demand is there, but the supply isn't there in the way that it was before. So people have been able to fill this niche. So I think there's still huge opportunity for people to be science reporters. Whether you want to be a debunker, I mean, it just depends on your attitude. I mean, there's like, you know, Professor Dave does a great job of debunking. Look at Simon Dan does a great job of debunking. Godless Engineer. I mean, there's a ton of channels that I think do a great job of debunking. Some are more in your face than others. And then you've got people like me who do the reporting side. And I think there's tons of room for that as well. So I would say there's tons of room for all of that and more. I just don't think that you can look to be part of a larger media institution in the way that you could in the past. You've kind of got to go your own way. And that requires a certain level of entrepreneurship at the same time that you are doing your reporting. Menelik Henry Dreyer. What other interests do you have outside of space science? So many. It's funny, when I started Universe Today, I was working for a web development agency in Vancouver, and I had a lot of crazy ideas about building websites. And I would sort of talk to my clients about these ideas, and they'd be like, I don't understand, I haven't seen any examples of this. Can you please sort of show me how this works? I'd be like, okay, fine, I'm just going to do this myself. And so I built Universe Today as a chance to both explore one of my hobbies, which was space and astronomy, which I'd always been a fan of even as a little kid, but also to practice my theories about what it takes to run a website in this modern age, that they have to be updated on a regular basis, that there's got to be a certain amount of personality that comes through, that you want to offer people different ways to receive this information, that it's not about building the website, it's mostly about maintaining the website. But it was a fluke that the website was about space. I happened to be reading The Case for Mars by Robert Zubrin and Pale Blue Dot by Carl Sagan, and so I was sort of inspired by space at the time. I'm like, okay, space, that'll be the website, but it's just be a side project. Who cares? But pretty quickly I learned, no, this is all I want to do with the rest of my life is write about space and astronomy. Now I just have to figure out how to make a living from it. But I had tons of other hobbies. Like I could have, I was really into video games, and I think that would have worked just fine. I would have been a video game journalist instead of a space journalist. Mountain biking, hiking, living on Vancouver Island, cooking, science fiction, reading, traveling, any of those could have been what I ended up publishing. I'd say like right now, I'm super into restoration of the natural habitat. So where we live here on Vancouver Island, we've got a pretty big chunk of land, but it was forested. And so all of the trees were cut down, and now it's just a whole bunch of tightly packed Douglas fir trees planted a meter apart, and it's not healthy. And so I'm out there all the time with a chainsaw cutting them down and just imagining like, what would be cool if we opened up more area and I planted other stuff and I brought in native species and there's birds and ducks and all kinds of stuff. So I found snakes and lizards and newts and different kinds of plants, rare plants. So that's what I'm, I always ask people like, what are you obsessed with? That's what I'm obsessed with and have been for the last couple of years right now. And I'm sure, that would be someone asked me in another QA, like if you didn't do Universe Today, what would be your website? And it would an alternate universe Fraser Cain. And it would be probably a website about, or video series about living on Vancouver Island and just like how amazing this place is. So, and who knows, if I have time, I'll do that too. I don't have time. Some mad random person. Are all the galaxies moving away at the same rate, or are some faster than others? So at the closest scale, the galaxies are moving in various random directions. So Andromeda is moving towards us. The Triangulum galaxy is moving roughly towards us. All the other galaxies in the local group are all kind of moving around each other. But outside of the local group of galaxies, the galaxies that are in the 10 million light years away range and beyond, they are moving away from us. And the farther the galaxy is, the faster that galaxy is moving away from us. And this was the amazing discovery that Edwin Hubble made a century ago, was as he measured the distance and the rate of movement of all of these galaxies around us, he found that the farther the galaxy was, the faster it's moving away from us. Until at the farthest reaches, galaxies appear to be moving faster than the speed of light away from us in all directions. So right up close, it's kind of random just because we're all locked together in gravity. But beyond that, it's a very smooth relationship. The farther it is, the faster it's moving away from us. And yet, if you go anywhere in the universe, you'll see the exact same thing, that all the galaxies are moving away from you. How weird is that? Rutger von Odenhoven. How much dark matter is there in our solar system? It all depends on what dark matter is. So if you assume that dark matter is a particle that is evenly distributed across the entire dark matter halo, the total amount of dark matter that's in the solar system is a surprisingly small amount, probably about the mass of a small asteroid. So it has almost no effect if it's here in the solar system. But most of the area around the galaxy is not solar systems. It is the empty space. It is the interstellar space in 3 dimensions between star systems. And so that's how you get this thing that accounts for 10 times the mass of the matter that we can see, is the invisible mass of the dark matter. Goat Lord, how big does an object need to be to hold an atmosphere, or does it have to do with its magnetic field? I think we need to sort of ask ourselves, how big does an object have to be able to hold an atmosphere for a long time? So, for example, you have Mars, which is relatively small compared to the Earth. It's like 1/3 the size, 1/10 the mass. So it has much less gravity, and it is not able to hold on to its atmosphere. It doesn't have a magnetic field, so it's not able to redirect the solar wind particles, and it lost most of the mass of its atmosphere to space a long time ago. And then we look at another example, say Venus. Venus also does not have a magnetosphere, and yet obviously Venus has an incredibly thick atmosphere. It's much closer to the sun than the Earth is, and so it's receiving a lot more radiation from the sun. It's getting hit by the solar wind a lot more strongly, and so, but it's able to hold on to its atmosphere. But all of the hydrogen was blown away from Venus's atmosphere. So the heavier carbon dioxide sticks around, but all of the water molecules were broken up by ultraviolet, and the hydrogen atoms were blasted away into space. And so without that protection, it still has an atmosphere, just a carbon dioxide atmosphere. But we could put an atmosphere at the moon that had the density of the Earth. It would just be a lot smaller on the moon. And it would hold on to that atmosphere for about 10,000 years. And so you'd only need to replenish it once every 10,000 years. So it's really more of a question of time. How long do you want that atmosphere to remain? I always think it's such a cool idea that you could terraform the moon. All right, those are all the questions we got this week. Thank everyone who put your comments into the YouTube chat, as well as everybody who joined me for the live show. We do the show every Monday at 5 p.m. Pacific time. It is twice the length. It's like 2 hours long, and yet we edit it down painfully into the QA that you're watching right now. So if you want the full experience, come and join the live show. Monday, 5 p.m. I'll put a reminder here on the channel. I'm going to continue directing you towards small channels that deserve your subscription. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, Antonio Lofilara, David Gilton, Dougie Stewart, Dustin Cable, Jeremy Mattern, Jordan Young, Josh Schultz, Mark Anstis, Paul Rohrbach, Stephen Krasaki, Stephen Feiler-Munley, and Vlad Chiplin, who support us at the Master of the Universe level, and all of our other patrons. All your support means the universe to us. All right, so for the last couple of weeks, I have been directing you towards other channels that I think you should definitely check out. And I had a couple of people recommend this channel, and I really like it. So the channel is called Eager Space. And on Eager Space, they cover a lot of concepts in spaceflight. For example, what does it cost to hire an astronaut, or the story of the Vulcan, or what's going on with Starliner. So I think, a lot of channels are focused with laser rapt attention on every single thing that SpaceX does, but it is a big industry of spaceflight. There's a lot of other companies that are doing a lot of other interesting things, both currently as well as historically in the past. And it's great to see a channel that is considering all of this other stuff that has happened now and in the past, as well as sort of dealing with questions like, could the space shuttle have ever gone to the moon? So check out Eager Space, and definitely keep sending me your recommendations for small channels, less than 10,000 subscribers, that are doing a great job of talking about space and astronomy and other scientific concepts. All right, we'll see you next week.